Hey everyone, in this video let's go through question 116, populating next right pointers in each node on Leetcode. This is part of our Blind 75 playlist on Leetcode, so let's begin. In this question you are given a perfect binary tree where all the leaves are on the same level and every parent has two children. The binary tree has the following definition: is a val, a left and a right pointer, and a next pointer. You want to populate each of the next pointers to point to the next right node. If there are no next right nodes, then the next pointer should be null or none, whatever. Initially, all of them are set to none. So basically, here is the tree that we are given. We can see that it's a perfect binary tree in that each of the parents has two children, and the leaves, obviously, since they're not parents, they won't have any children. But the binary tree is completely filled, and it's all the same level, essentially. So it's not like it's imbalanced. It's completely balanced here. What we want to do is that we want to link 2 to 3, 4 to 5, 5 to 6, 6 to 7. So basically just going on the right hand side, and we can see that 1 actually doesn't have a right hand side neighbor, so we don't do that. So let's take a look at how we can make this happen and what might be the approach that we want to look over here. Well, in the start, it might seem like this is actually like a tree problem, right? Like where we have to do some sort of recursion or something like that. But if you really take a look at what we are doing here, all we really need to do is go level by level, right? And if you think about this, so let's say we start off at this initial level here. When we process the node 1, which happens to be a root in this case, well, there's really nothing else we can process here. So we can move on to level 2. And in level 2, we'll have these two nodes, right? And then what we can do is we can process 2, we can process 3, and then we can basically join them together. We can then go on to the next level, and I'll redraw this. Go on to the next level. Here we will process 4, 5, 6, and 7, and then we'll simply connect them up. Now, the question is that how do we process level by level, right? Here, we're just processing the level 0 or level 1, you can say. Let's say this is level 2. Let's say this is level 3. So how do we process level by level? Well, one of the algorithms that does ring a bell here is breadth first search, right? In breadth first search, essentially what you're doing is that you are going level by level. So maybe you're at this node over here, then you will expand to this level, expand to a level around it, expand to a level around it, etc. And you can see that that's basically the same thing we're doing here. Start off at this level here, and then we expand here, and then we finally expand down here, and then if there's more, we expand even below. So the best approach here is actually just to use breadth first search. And let's take a look at how we can start to code this, and then I'll add in some of the details as we start to coding. But let's get into the code part of it. So first of all, looks like root might be optional. So we want to handle the case where it does not exist. So in this case, we can just do like if not root, then we'll just return root here actually, because it looks like it's passed in as an array, right? So it wouldn't make sense for us to actually just return this. Let's just return root here. Now, what we want to do in our breadth first search is, here is a general format that I like to follow. This is what kind of works for me for the problems that I do in breadth first search. So in breadth first search, as we know, we want to have a queue. And the queue, it'll start off with just the root, right? It'll just start off with the root, which in this case, let's just assume it's 1. Then we have our while queue. So this basically makes sure that we continue looping, we continue performing the breadth first search until there are no more nodes to process. So basically, in breadth first search, if we want to expand level by level, then what I really need is at any certain point. So let me erase this. At any certain point, I want to go back. At any certain point, if this is the queue, right? This queue has size 1. Size 1. If this is the queue, has size 2. If this is the queue, it has size 4. Basically, the point I'm trying to make here is that whenever we add onto the queue, or whenever we perform an iteration of the breadth first search, we only want to process the amount of elements that are in a specific level, right? So the first time we do it, we just want to process this much, just one node. The second time we do it, we'll add in these two nodes, and we just want to process them. The third time we do it, we'll add in this. Actually, if you think about it, when we're at the 2, we'll add in 4 and 5, right? So by the time we add in 4 and 5, in the queue we already have 3, 4, and 5 left. But actually, we're only going to process 2 and 3. And so then in the final level, we're just going to process 4, 5, 6, 7. But the point I'm trying to make here is that we only process the amount of nodes that are on each level. It's possible that our queue will actually be larger at any single point, but we only process the amount of nodes that are on a single level. That's how we do the breadth first search. So one way we could do that is we could actually calculate the size of the queue. And then one thing I want to do is I will have a loop that goes from 0 to size -1. And if you think about this, let's think about an arbitrary level. Like let's say we're on level 2 here, then the size of the queue will be 2, right? And essentially I want to loop going through these two, but basically what I want to do is I want to q at I dot next is equal to q at I plus 1. So what is this going to do? This will basically add a link to the 3. And the reason I have a -1 here is because 3 doesn't actually have a next pointer, right? So we don't want to go out of bounds here. So basically, if we just did something like this, then what we will have is we will have 2 linked to 3, and then we'd have 4 linked to 5, 5 linked to 6, 6 linked to 7, etc. That's the point of the size variable here. Now, one more thing we actually need to do is that let's say when we start this off, we'll just go ahead and we'll process the first node, right? Which is just the root in this case. So we'll just go ahead and process the root, which is just this one here. But now we need to add the root's children. So what I can do now is I can actually go through the queue again. And this time I will consider all of the elements in the queue. And basically I will add their children. So I will do if, or actually first thing I need to do is I need to pop the element, because in breadth first search we always pop the element from the front. So I will do pop from the front. And you can also use a dequeue here, but queue is, I guess, just fine for Leetcode. And here, so we'll have the elements, so we'll have the number 1 here. Now we want to add the left and right childs of 1. So we can do if cur.left, and we will add it. So we will do append cur.left. Similarly, if cur.right, we'll append cur.right. And we have to add in this check here, because if we're at the leaves over here, we don't want to add none, right? Because they have no children. So we don't want to do that. And basically, that's all there is. In the end, all we will do is we will return root. Let's go ahead and run this. Submit it. We'll see that it works. So basically, in this question, what we're doing is that we're performing a breadth first search here, and the time complexity is basically just the amount of nodes that are in the graph, right? The amount of total nodes, we'll just process them one by one. And also the space complexity, you can kind of argue that the space complexity here is the same thing here, right? Because at the maximum amount, well, actually here it's a perfect binary tree, so it's a little hard to calculate. But because at any certain point you won't have the entire graph inside of your queue. But if you say it's something bounded by like total amount of nodes, then that's also fine. But the point I'm trying to make here is of this size over here, right? Like we need to only process the amount of elements that are in the queue at a certain level. So let's actually just take a look at this before I end the video. Like let's say if I was to remove this, and let me just all of this. And here I will have my queue, right? Here are my queue. In the start, we just have the element 1, right? And so here the size is 1. And what we will do is after we process the 1, we will add in 2 and 3. And at this point, the size is 2. Then what we will do is we will pop 2, right? We'll pop 2. And here actually we pop 1 and then we add in 2 and 3. But here we will pop 2. So now size still 2. The elements in the queue is just 3. After we pop 2, we will add in 4 and 5. 4 and 5. So you can see here that the size is still 2. So the only thing we will process in this level is the 3, because we've already processed the 2, which is size 1, and now I'll process the 3, which is size 2. But you can see that the queue is actually total size 3 right now. But it would be incorrect for us to process this now, because then it would link 3, 4, and 5, which is not correct. So then we'll process this one. And then finally, we will pop 3 here, and then we will add in, actually, 4, 5, 7. And then this iteration actually finishes because we finished size 2, and then here we'll be size 4. And so that's the entire point of the size variable, which is important to have in breadth first search. Anyways, I hope this video helped.